welcome to our first attempt at doing a video lesson for HL Mathematics. We're going to start with the vectors and all their operations today, with specific looking at the addition, subtraction, and scalar multiplication. And then at the end we'll look at one example where we do addition with scalar multiplication. The steps we're going to show today are for those people who have taken physics you're probably familiar with and have seen. After this lesson we will go on to do algebraic means for basically the same things. And hopefully you will see just how much better mathematics is than physics. So here, let's get started. Vector addition. We're looking at these two vectors, A and B, on our screen right now. And we're going to add the two together. And I'm going to show you a series of different, or a couple of different ways of doing it. One feeds off the other. Physics, I'm sure they only showed you one way. But I'm going to show you the other because it shows a nice fact about vector addition as well. Now down here in these bottom piles I have copies of vector A and vector B. Now they're copies, but they're also what we call equal vectors. Equal vectors will have the same direction, as you can see if I put them right over top of each other, the same and the same magnitude. They are exactly the same vector, hence they are equal vectors. If this was vector C, I would say vector A is equal to vector C. But we're just going to call it vector A. Now to do vector addition, I'm going to start by putting the two vectors A and B in what's called a tail-to-tail manner as I try to get it lined up. So I'm just going to label, this is vector A, this is vector B, and this is in a tail-to-tail. What I want to do with these is I want to complete a parallelogram with them. So what I'm going to do is I'm going to take vector B, another copy of vector B, still vector B, and put it on the head of vector A, like so. And then you take another vector, copy of vector A, and put on the tail of, on the head of vector B. So here I've got the head to tail, and it finishes off in a head-to-head manner. And as you can see, I've created a parallelogram. The answer, A plus B, is that diagonal right there. So this is vector A plus B. A plus B. Now, that is the triangle law, or the parallelogram law of addition. Alright, so that's the parallelogram. Now what I like about this, I'm just going to write in a vector A here. So if I follow on the top here, I got vector A followed by vector B. That makes A plus B. But if I look on the bottom, I get vector B plus vector A. I'll try to scribble in. And you can see what that shows, the parallelogram law. It shows that vector A plus B is actually vector B plus A. That's a very nice little, handy little thing to know. Now, as we look at this parallelogram, you can also see a quicker way of doing it. You know, the physics people are trying to ruin our lesson.
Okay, enough. I'm sorry I said physics. Okay, enough. All right.
So yeah, we can do a triangle. As you can see, the A plus B, which is called the resultant, usually we represent with a big R, okay, is really this line plus that line in what we call a head to tail, right there, manner. So that's what we're going to do next. We're going to show it as a triangle law. So let me take a copy of A. I would then put a copy of B on the end. And what I'm going to do is I'm just going to clone this one just to show you it's exactly the same answer. So we get vector A plus vector B, and this is the result of A plus B. It's the same thing. Now this is in a head to tail manner. I'm just going to shrink that down. Put it right there. Head to tail. So there's two ways that we can actually add two vectors together, but we generally use just the triangle because it's really the same thing as a parallelogram and it's quicker. But again, the nice thing about this parallelogram is it does show that A plus B is equal to B plus A, an important result. So in vectors, it doesn't matter the order that we add them in, we will get the same result. All right, let's look at vector subtraction. I've taken the same vectors, A and B. I've represented vector B, though, down here, these guys here in red and going in the opposite direction. That makes them negative vector B. Okay? You will notice they have the same magnitude, but they have opposite direction. Hence, we call them negatives. So, if I was trying to do A plus B, there really is no vector subtraction. What we do really is vector addition. But if we've got A minus B that we're trying to figure out, what we actually do is we add them. And we add the negative of B. So that means we do the triangle law. We're going to take vector A, label it, vector A, and we're going to subtract vector B, or add on the negative of B. That makes the resultant from there to there. There is vector A minus vector B. Okay? That's how you do vector subtraction. It's really not involved at all. So we just take we add the negative, and you saw the triangle law. So it's vector A, and then we're going down negative B, so that makes A minus B. Now that makes for something that can be a little bit interesting to look at, is if I took vector A, because you might be wondering how are A plus B and A minus B related. There's vector A, and I'm going to add them on the end. And I'm also going to add on the negative of B. I'm going to duplicate this guy. You can see him right there. Of course, this is not a perfect diagram, but there you go. There you can see them related. Here we've got A minus B. Here we've got A plus B. This is vector A, this is vector negative B, and vector B. Right? So that's how you can actually see them related. Let's go on again. Here's another diagram. There's nothing. Well, there's two lines parallel. There's vector AB, or sorry, side length AB is parallel to DC. Write that in. What I want to look specifically at is vector AB. So vector AB, when I write it like this, that represents the vector from A to B. Now, there's other ways I can write or get that sum of A, B, that length, is by adding a couple different vectors. And what we can do is triangle law. So for instance, if I want vector AB, I can use the point E. Vector AE would go from A to E, and vector EB would go from vector E to B. So I'm just going to use a different color here. So if I want vector AE, and I take vector EB, B, I get, you highlight it. No way you won't see me scribble so much. And I can't really do that. We get vector AB. Okay? So if I were to write that down, I would write AB is equal to vector AE plus vector EB. There we are. There's our first one. Do you see another way of writing down AB? Take a moment and write down as many ways that you can see of getting vector AB. So let's continue on. AB can be also drawn by using point D. Hopefully you got that. Vector AD and then adding on vector DB. It creates another triangle. So that's our whole clue, our whole key here, is that we want to add to make triangles, but at long side is always going to be the summation of two of the sides of the triangle. Did you see another one? How about AC? Could you use point C? So AC plus CB. There's another way too. You could use more than one point. It's not really triangle law, but well, I guess it really is, but you might not see it as a triangle because it's not a triangle. But I could use points D and C. I could go vectors AD plus vector DC plus vector CB. You can see almost like the D's will cancel out and the C's cancel out, so you get A to B. One other way you could do, well, there's actually lots of ways, but I'll show you one other way. I'm not sure if anybody wrote this down, but remember we have negative vectors. So EB is actually the same as negative BE. So where I have AB is equal to AE plus EB, I can also do it as AE plus, or the negative vector, I can do minus vector BE. That would also create. Okay, I'm going to stop there. I mean, I could go on forever. I could do all kinds of different ways around and represent all kinds of different vectors in those ways. I'm going to try this question here. Right, ambitious hiker walks 25 kilometers west. So we're starting here. And then 35 kilometers south. So there's there. And what we want to do is we want to find the magnitude of their displacement. Okay, how far they've gotten, their resultant vector. It's an R. And we want to find the angle it makes with the due west direction, which is that angle there. So it's a right angle triangle because it's west and then south. So we can just use Pythagorean theorem. Notice I've got absolute value around the R. The absolute value will represent the absolute value of a vector is its magnitude. That's your magnitude. So if I'm doing the magnitude here, I'm going to go 25 squared plus 35 squared, and then I need to take the square root. So the magnitude of our 41.3 kilometers. Now what's the angle? Now we've got theta here. We've been given the 25 and 35, we have the R. So we have all the lengths now. The only thing is the R might be slightly off in that it's been rounded off. I would recommend you use the given information, which is the 25 and 35. And for theta, that would be the tangent. So the tangent of theta is 35 divided by 25 gives 54.5 degrees south of west. Okay, here's a second question, very similar type of question. A boat hits directly across a river with a velocity of 12 meters per second. river flows at 6 meters per second. So there's my river flowing. What we make that blue? Oh, I've already grouped them. 6 meters per second flowing that direction. So we want to find the magnitude and direction with respect to the shore. Here's the shore. You'll notice that because those shores are parallel and the current is parallel to the shore, we're assuming that creates a Z pattern, which makes these angles actually equal. So we're going directly across. The current's pushing the boat that way, so this would represent the actual direction of the boat that it would actually go at. So again, we've got a right angle triangle here, and so that means we can actually find that magnitude again the same way. Let's make that an R. So our resultant squared would be 12 squared plus 6 squared. So once we take the square root, 13.4 meters per second. Now what's that direction? Again, we can just use tangent. It's better than using sine or cosine because we're using exact values. The tangent of alpha in this case is 12 over 6, which is 2, so alpha should be 63.4 degrees. Good. All right, let's talk about scalar multiplication. Scalar multiplication is like taking 2 times a vector, 3 times a vector, that sort of thing. You can see I've got vector A here and I've got some copies. If I were to put this A onto the end of it, what's the length of our magnitude of our vector now? Well, obviously it's 2 times the original vector. It's got the same direction, so that would now be 2 times vector A. If I were to add another vector, same length, how long is our vector now? Well, it's now 3 times vector A. Still parallel. If I were to add the last vector I've got here onto the end, of course now it's 4 times vector A. Still parallel. Still parallel. That's a very important thing here. When we multiply by a scalar, and a scalar is any number, any real number, then we're looking at never changing the direction. If I take a vector A and I multiply it by some k, where k is an element of the real number set, it does not change direction. All it does is it changes the magnitude. The magnitude is k times the magnitude of A is now the magnitude. So that's kind of a nice, easy thing to remember. So here's a little bit of a summary. So if A is, and this is right from your textbook, if A is a vector and K is a scalar, then Ka is also a vector and we are performing scalar multiplication. If K is greater than 0, then Ka and A have the same direction. I've shown it down here. Here's vector A, and I've multiplied it by some K greater than 0. It still is parallel, still has the same direction. It's got a different magnitude. K is less than 1 in this case. I can tell you that much right now. You can think about why that might be. But the key thing here is they're still parallel, and that's very key. Over here, I've multiplied by some scalar m. Now, m just happens to be, and this is wrong, m just happens to be less than 0. And it changes the direction, as you can see. Now, I'll ask you, is m greater than 1 or less than 1? That's something for you to answer on your own. One other thing I want to show you, and it shows up later on in the chapter, but I think it's important to show right now, is the idea of what's called a unit vector. A unit vector is any vector with magnitude of 1 unit. Okay? And that helps us when we're trying to solve a question like as follows. Two unit vectors A and B make an angle of 60 degrees with each other. Calculate the magnitude of 2A plus 3B. So I'm just going to pull out magnitude or vector A. We'll say that's 1 unit. And vector B. So there's vector A and vector B. And I know that's 60 degrees between them. I'm just going to copy this and move it down here a bit. Now I want to do 2A plus 3B. So I'm going to just, so that means it's going to be a triangle. 2A, so I need 2 vector A's together and I need 3 vector B's together. So I'm going to do some cloning here. I need 2 vectors A's. I've already got 1. So let me put another one on the end. There's 2A. And I need 3 B's onto the end. Now I'm not going to use this B, so I need to clone a few times. I need 3 of them. So I'm going to put them on the end. So that's the head to tail manner of triangle law of addition. If I can get it lined up. So that, if I just change it, nothing exact here, of course, this is 2A. This works out to be 3 vector B. And our resultant will be there. So this is 2A plus 3B. Now remember, these are unit vectors. So this length here is actually 2. This length here is actually 3. Do I know this angle? Well, yes, I do. This angle is 60 degrees here, which makes this 120 degrees because they're 2 parallel vectors out here, and it's the C pattern. So, cosine law will do it. So the magnitude of 2A plus 3B all squared would be 2 squared plus 3 squared minus 2 times 2 times 3 cosine of 120 degrees. I'll let you finish it off. Approximately 4.4. Okay? That should be about it. Hopefully we've gone over a few things that made things a little clearer. If you're still fuzzy on a few things from the first unit on that independent study, then please ask questions. Okay guys, that's it. Everybody get out. Come on. Time to go. Come on. Let's go. Go, go, go. That's better.